Hey there, educators, and welcome back to the Make Math Happen podcast. I'm your host, Lanisha, and let's take a moment to think about how we're doing. I know this is atypical for the start of an episode, but I want you to ask yourself, how am I doing? And I want you to sit with whatever response comes to mind because I don't know about you. I don't know about your school and your classrooms, but we have a lot going on in our school building. So much so that right now it is super important that we stay grounded, that we are taking care of ourselves, that we are listening to our bodies and responding to what our bodies and our minds are telling us in that moment. Okay. So I want you to take a moment and think about how are you right now? Okay. All right. So now I want us to connect some dots. Now that we know how we're doing, let's connect some dots because I always want to make sure that we're activating our prior knowledge, remembering why we are here because we just came from somewhere, right? So in December, we focused on seeing math. Geometry teaches students to notice structure, to be able to reference points, alignment, and scale. In January, we shifted to understanding math. We slowed down with number systems and really talked about how our numbers composed, where do those numbers live in relation to other numbers, and really the overall relationships from one number to the next. In episode 1 of this month, we reframed ratios as relationships. In episode 2, we clarified what we were comparing. Is it a part to part situation? Is it part to whole? Is it unit reasoning? And today we're going to make our next move. We are not just identifying ratios, we want to reason with them. This is where proportional reasoning becomes visible. And this is where representations become essential. So, what is proportional reasoning anyway? I'll tell you what it's not. It is not just you setting up a proportion and telling kids to cross multiply, because what really does that mean? And why really does that work? Proportional reasoning is the ability to recognize when two quantities vary together multiplicatively. It is also the ability to predict how one quantity changes when the other changes. Proportional reasoning is also the ability to reason about unit rates and scale factors and also check magnitude and reasonableness. It builds directly on multiplicative reasoning, unitizing, geometric scaling, and understanding the number line. If ratios are about relationships, then proportional reasoning is about using those relationships to solve problems. If we want students to reason proportionally, we must make the relationships visible. Tape diagrams make part to part and part to whole relationships explicit. They show alignment, they show equal grouping, they show scaling, and they show structure. Tape diagrams are geometric. They rely on partitioning space and aligning units. When students can see the bars grow together, proportionality becomes logical. But I'm going to pause here and say that just because we present students with these models does not mean they're going to automatically understand them and what they represent. This is where our think alouds really show up and really help students see the point of it all, right? Because sometimes things that become automatic for us or feel automatic to us is because we've been dealing with it for so many years. Some of our students have seen things, but they haven't really had time to understand them. I mean, the time has passed, the years have gone, but they didn't have enough time to go deeper and make sense of why these representations work. So just keep that in mind as you are showing these tape diagrams. Ratio tables make scaling visible numerically. Students can see doubling, tripling, having, unitizing. We oftentimes use the arrows to show that, right? They make multiplicative structure explicit. This activates mathematical practice 7, where we're looking for and making use of structure. It activates mathematical practice 2, where we're reasoning abstractly and quantitatively. Students begin to notice patterns instead of relying on formulas. We want students to see those patterns. We don't want students to have to try to remember, well, what do I do in this situation? Is this the time where I divide first or do I multiply first? What do I do? We don't want them doing that. We want them looking for patterns. Have you ever asked a student to go to the board and the first thing they do is grab their paper? Can I take my paper up here with me? Oftentimes, I'll tell them no. Because if you really understand, then you can go to the board and you can work through it without looking at what you did on your paper because you understand it, right? Well, students are so reliant on what's on that paper sometimes. They're so reliant on remembering what we've told them that they are not thinking. And we don't want to steal the thinking from students, right? We want to encourage the thinking. What is it that you see? And I think that's really the heart of the work when we think about problem-based learning. And I know there's a lot of criticism around problem-based learning and discovery and exploration. But when you get to the middle grades, you really want to know. And actually, let me pause. It's not just middle grades. It's probably in primary as well, right? We want to know, what are students seeing? What makes sense to students? What can they connect to this new learning from the learning that they already hold, that they already own? What can they connect here? So you want to see what students can come up with. If they are tied to their notes, if they are tied to their anchor chart, if they're tied to what's on their paper, then do they really see the patterns? I want us to really think about that, right? Because in the last episode, I told us that I was toying around with the idea that if we're looking for evidence of understanding, then when students are working things out, we should see small little distinctions from maybe what we told them, not in an incorrect way, not in an inaccurate, messy type of way, but in a way that shows us that they are thinking about how this new learning, this new material connects to what they already know. Okay. So keep that in mind. Keep that in mind. Okay. So that's ratio tables. Double number lines connect geometry and number sense directly. They align two quantities, they show scale visually, they preserve distance relationships, they make unit rates visible. And when extended to the coordinate plane, proportional relationships become linear graphs. This is where ratio meets slope or rate of change. A proportional relationship becomes a straight line through the origin. Geometry is still doing the work. We got the alignment, we have the iteration, we have the scaling. Okay. Now, one thing that I want to emphasize is that when we think about rate, we're not talking about divide one number by another. Oftentimes, students don't know what to divide when we reduce the idea to an operation, or what to multiply for that matter. They end up memorizing steps, but they don't truly understand what's happening to the quantities. And as a result, they need constant support instead of making sense independently. You ever had one of those situations where you told a student something time and time again, but they're steadily coming back to you for more answers. They're steadily asking you more questions. They may even not be starting the task or the assignment because they don't know where to start. It's because they are heavily reliant on your scaffolds, on the questions that you ask, on the things that you highlight for them, on just you being there, because they have not developed that ability to stand on their own. Okay. So again, I want us to think about when we're teaching things and how we're teaching things, to make sure that we're giving students an opportunity to think and not just listen to us think. Obviously, teacher think alouds are important and they have a place and they should be happening. But the teacher think aloud should not be the only thinking that's happening. All right. So a rate is a multiplicative comparison between two quantities. Unit rates answer the question, what does one unit of this represent in terms of the other? And this is where our language matters. If we begin introducing the ideas of independent and dependent variables as early as appropriate, and that's usually around sixth grade, we end up curating the thinking that is necessary for students to later graph relationships with confidence. When students understand that one quantity depends on another, that the relationship is consistent, that the rate tells us how they vary together, then graphing is not new. It is a visual extension of reasoning they already understand. If we only teach division, students compute. But if we teach variation, students begin to reason. And that's what we want. That's what we want. And again, when we're introducing terms like independent variable and dependent variable, guess what else makes sense? Students can then start to think about, how are these things related? And what is the reciprocal relationship that also exists between these two quantities that are related? So that's important as well, right? So if we are building proportional reasoning, we should hear students making sense of the problem before computing. And that is mathematical practice one. We should hear students explaining how quantities vary together. That is mathematical practice two. We should hear students choosing and using representations strategically. That is mathematical practice four. We should hear students identifying multiplicative structure. That is mathematical practice number seven. And we should hear them checking to see if answers are reasonable. That is mathematical practice number six. If students are only copying procedures, we will not hear any of these things. And that brings me to a classroom example. I was in a classroom recently where the teacher was using the three reads routine. She asked, what is the situation about? What is countable or measurable? What strategies might we use? But only one student was responding each time. The others were waiting And guess what they were waiting for? They were waiting for answers. They were waiting to copy annotations. They were waiting to be told. Assignments were being completed, sure, but thinking wasn't happening across the room. So here's the tweak that we're trying in the coming week. After each question, she will now give students 60 to 90 seconds to stop and jot. During that independent time, she's going to make labs. After that timer goes off, students can turn and talk. She's going to make another lab. This happens after each question, and the teacher is going to be constantly moving, constantly listening, constantly collecting student ideas and thinking about how to use those student ideas to further the lesson. And guess what else is happening? As she's moving around the room, she's going to announce what she's looking for. So, for example, after the first read, and she asks those students, what is this situation about? And she says, I'm going to give you 60 to 90 seconds, and she's going to have to determine that based off of how that class works and think about how much time they're really going to need for that. She's going to say, I'm coming around and I'm looking for your underlined words signaling what the situation is about. For that second read, she's going to ask them what is countable or measurable in the situation. Before she starts her lap, she's going to announce, I am looking for circled quantities. Your circles should include how much and of what. Because a lot of times when we ask that countable or measurable question, students are only circling numbers. And then when it's time to talk about it, they have no idea what those numbers represent. Third read, what strategy are we going to use in this situation? Or what's in relationship to one another, right? Remember we talked about tweaking that last question during the 3 reads, depending upon what is the task that we're involved in. So she's going to announce, I'm looking for the model that you're going to use, and I'm looking for the labels that show what is in the relationship and what that relationship is. This is very clear what she's looking for. She's looking for understanding, okay? She's looking for their ability to read this. They've already read it at this point 3 times. Their ability to look at that text and see what are the quantities that are in relationship. And fortunately, the students have already circled it, right? They've already circled it. They've had time to talk to a peer about it so they can refine their thinking. And now we're going to the model. Total participation builds total reasoning. If we intend to build ratio reasoning and proportional reasoning, we cannot let a few eager students do the thinking for everybody. We got to have all hands on deck. All hands on deck. Now, the reality is that this may slow your lesson down. Absolutely, it probably will. But are we more concerned about the speed of our lesson or the depth of the learning? That's really what you have to ask yourself. Am I concerned with speed or depth? Okay, so let's slow down here because this next part matters. Geometry strengthens spatial reasoning, right? Number sense strengthens magnitude reasoning. When students use tape diagrams, double number lines, coordinate planes, they are practicing geometric alignment and numerical reasoning at the same time. So how do we intentionally build these skills? Because I know you're thinking, okay, a lot of the issues are students' numeracy skills, okay? So let's think about how can we build the intersection of skills, right, that show up when we are doing this work. We have to give students opportunities to choose a model. Let's choose a model that makes the most sense for me to use here, that is the most efficient, that I feel the most comfortable with. Then we need to give students a chance to create models. They need to practice creating models so they can understand, okay, this is what I need to do whenever I'm working with tape diagrams or I'm working with double number lines, whatever the model is, we need for them to understand, what does it look like? What do I need to consider whenever I'm creating it? Okay. And then we need to give students an opportunity to use a model to explain. Okay. So I'm using the tape diagrams to show the relationship between these two quantities. I should be able to articulate the relationship that I am attempting to display, attempting to make visible. Then we can layer fluency practice on top of reasoning practice. And I want to make sure that I am clear. Fluency is not just speed, okay? Fluency looks for accuracy, efficiency, flexibility, thoughtful decision making. So, how do we build this? So, let's say that students are solving proportional problems and they're using tape diagrams. We might ask them to represent that same relationship using a different model. So, maybe we ask them to show it to us in a ratio table. So, that's going to help us see if they are flexible. Then we may ask them to graph it, describe it verbally. And then we are going to ask them to check for reasonableness. Does what you did make sense? Does the answer that you got make sense? And then they can have some time to think for themselves, which of these models is the most efficient for me to use based on this situation. One thing that if I had my way that I would want to happen is I don't want students to feel like every single time that I do this, I have to do it this way. I want them to think about, well, what are the numbers that I'm working with? Because if I'm working with really large numbers, I'm probably not going to draw a tape diagram. I'm probably going to want to use a table because it's going to be easier for me to organize how one relationship is being scaled, right? It's going to be easier for me to show that without it being too time intensive. So that's what I want students to think about, and that's what I want them to understand about being flexible. That's from that geometrical standpoint, from the modeling it. When we think about number systems fluency, this is critical because we talk about this so much. When students are comparing quantities, when they're finding unit rates, when they're scaling relationships, they're operating with numbers, right? So if they're not fluent with multiplication facts, fraction to decimal conversions, place value reasoning, their cognitive load increases dramatically. So instead of thinking about the relationship, they end up thinking about the arithmetic. They get bogged down in that. And that's when the cognitive load is overloaded. And as a result, the reasoning suffers. They can't analyze anything. They can't think about connections because I'm trying to figure out what I can multiply this by to get to this next number, right? So in class, obviously, we can provide a calculator strategically because doing so supports access during complex problem solving. But somewhere in our ecosystem, whether that is for homework, whether that is in small groups, whether that is during an intervention block, whether that is in after school tutoring, students need structured opportunities to build numerical fluency. This does not mean mindless drills. This does not mean giving them pages and pages of multiplication tables where they're just filling in the blanks. No, it is intentional fluency work that strengthens multiplicative facts, fraction decimal equivalents, place value shifts, mental math with unit rates. And remember what fluency is: accuracy, efficiency, flexibility, thoughtful decision making. When students are fluent, they have more cognitive space available for reasoning. So building fluency fills gaps while reducing cognitive load during problem solving. This is not an either or situation. It is representation plus fluency. It is reasoning plus automaticity. When number sense and geometry grow together, proportional reasoning becomes durable. So here's today's big idea. Representations make relationships visible. If students can see how quantities grow together, how units scale, how alignment preserves structure, how graphs represent consistent variation, they don't need tricks. They just reason. And when students reason, the learning transfers. The learning is transferring. So this week, I want you to try at least one of these. Require representations before calculation. Build 60 to 90 seconds of independent thinking into every reasoning question. Announce what you're looking for in student work and then actually go look for it. Listen specifically for a multiplicative language. Ask students to predict before computing. Ask them to justify whether answers are reasonable. And most importantly, I cannot emphasize this enough, do not move to formulas until students can explain the relationships without them. Next time, we connect proportional reasoning directly to linear relationships and slope. Same story, clearer vision. Talk to you soon.